In this section, we're going to cover the topic of sound intensity and sound level. And so you might say, well, why do we need to cover that? Didn't we already cover the equation of a sound wave, and we talked about the amplitude of the wave and all of that? And doesn't that sort of imply the amplitude or the intensity, so to speak, of a sound wave? The answer is yes. The information as far as the amplitude of a wave and how much energy that wave is carrying is conveyed in the amplitude of the wave. But let me ask you this. If I'm sending a wave from me to you, if it's a sound wave, in general, that sound wave is not going just from me to you. That sound wave is in general, if I have a speaker here or something, or my vocal cords, that sound is spreading out in all directions because the disturbance that my vocal cords make with the air is vibrating the air molecules, and the chain reaction of collisions actually occurs in all three dimensions. So if you were to imagine a speaker here, the ripple effect of the sound is spreading out as it goes far beyond you. So even though, yes, the amplitude of a wave, a sound wave, does tell you in general how intense that wave is, there's a little more to it that's worth exploring when we're talking about sound waves, because in general, if you have a speaker source that's putting out energy or power into the air, that power is spreading out. And so if I'm located a certain distance away from that source, I need to take that into account, because the intensity of the sound that I hear X distance away from the source is going to, depend upon how that sound is spreading out. So we're really going to focus on that. I need you to keep that in the back of your mind during this lecture, or in the forefront of your mind during this lecture, is that sound waves, when they go out there, they're spreading out in spheres, because we're going to see a lot having to do with spheres, in this section, because the sound waves are spreading out like that. Now, comparatively speaking to laser light or something like that that's very directional, this is going to be useful, but not as useful. We're going to really focus on sound waves as our analogy for this section here. So intensity and sound level. Let's go ahead and first talk about the word intensity, or the definition, in this case, of intensity. Intensity. Right? Now, everyone has an idea of what intensity means. In general, the more intense something is, the louder it is, the more vigorous it is, the more, in your face, the more oomph it has, or whatever. But in physics, we have a specific definition. We say the intensity I of a sound wave is the energy per unit area transmitted by the wave. By the wave. Now, don't let this language confuse you or scare you or whatever. The energy per unit area, what does that mean? Well, let's draw a picture to figure out what this means. If I have, let's say I have a little speaker here, a little loudspeaker, and this guy, he's making a disturbance in the air, and so those waves are really going to be spherical wavefronts that expand out and go in all directions, really. I mean, if it's a directional speaker, the sound is really going to go this way. But if you had just a point source, the sound is really going to go in all different directions. But for the sake of argument here, let's just say that the waves kind of expand out like this, and they kind of go out this way. And if it were a perfect point source, then they would be going out in all directions, but they're spheres, you see, because we live in a three-dimensional world. Now, if I were to look over here and stand over here a certain distance away, obviously you know that the intensity of the sound that you hear really far away is less than if I stand closer. I mean, that's just obvious. The reason that's the case is because this speaker is putting out so many watts of power, but those watts, as the waves go, they're spreading out, and so they're covering more of a surface area. If you can think of this wavefront as kind of expanding as it moves, it's covering more and more surface area as it moves away from the source. So the energy in this wave crest, so to speak, which is like a compression of the air, it's moving, is spreading out. So it's becoming less and less intense. So it really does depend upon the total surface area out where you're standing, because that energy is going to be spread over that surface area, if you can think of this wavefront moving as sort of like a sphere that's growing. So if I were to stand out here and hold up a square meter, let's say you cut out a cardboard box. Let's say you go out, you get a big giant box, You find a box, you cut out 1 meter by 1 meter square, so you have 1 square meter. And I have a source over there, and he's blaring out music or something like this, or a constant tone, sound. And that is obviously, there's a power that's coming out of that speaker. So we know that the speaker, you know, maybe it says 100 watts or something written on the speaker. That's the energy that that speaker is dumping into the air at that point, way over there, 100 watts. But ever so, you know, at the moment that those waves begin to leave, that 100 watts is now beginning to spread out among, you know, a sphere that's encompassed by however far away I am, right? So if I were to stand out here so many meters away and hold up a square meter and then measure the energy coming through that area, I would get what we call the intensity of the sound at that point. The units, so what I'm really looking at here, I'll get to the units in a second. The intensity is the energy flow through a unit area. That's exactly what I wrote above. It's just slightly different wording. Here I said the energy per unit area is transmitted by the wave. This is the energy flow through a unit area. So if you were to stand out there with a cardboard box that measured 1 square meter and you had some kind of detector that could measure how much energy in watts was flowing, or how much power in watts that was flowing through there, then you would have calculated the intensity. And so without proof, the intensity, because of this discussion I'm telling you here, the intensity I is always the power that the source is delivering divided by the area. And the area just depends on where you're standing. If I'm standing here, the surface area that this wavefront is encompassing is the entire sphere through there. And if I'm much farther away, then obviously the circle is much bigger, the sphere is much bigger, and so the surface area that that wave has spread into is much larger. So the farther and farther and farther I go away, if the waves are spreading spherically, the larger and larger surface area those waves are taking up, and so the less intense the sound is. And that is exactly why it sounds less intense when you're far away. Because when you think about it, if the wave is coming out of the speaker with a certain amplitude, why doesn't that, and if each collision is perfect, let's say, in physics we always talk about perfect collisions and all kinds of other perfect things, perfect pulleys, perfect friction. Let's say the waves were perfect. Each collision with the air molecules was perfect. And so if that's the case, if I make a sound over there and it propagates to my ear, why would it not have exactly the same amplitude of the wave as it travels from me to you? Well, you would think that that could be the case, but you know that it's not. In real life, you know, of course, the farther away you get, the lower the sound is to your ear. The reason is that that guy is disturbing the air, but that disturbance propagates in 3 dimensions. So as it moves farther away from you, the energy in any given square area that's passing you is getting less and less the farther away you get. Your eardrum is a little small, you know, flap of skin in there, maybe a square centimeter. I'm not even sure how big your eardrum is. It's probably less than a square centimeter in there. And that eardrum is the only way you receive sound. So the energy of the air must hit your eardrum. If I go farther away, the wave fronts are less intense because they've spread out so much. And the energy, the power that was coming out of that speaker when I'm here is being divided up over an area that's much larger than if I was here. So the intensity is lower the farther away you get. It goes by this equation. Now, I'm not going to prove this to you, but empirically in the laboratory, people have calculated that the intensity can also be written as 1/2 times the density of the medium you're in, like the air, times the speed of sound, times the frequency of the wave, the angular frequency, times the amplitude of that wave squared. And so the units that you're going to get here is what we talked about before, watts per square meter. So I know this kind of unit may seem a little odd to you at first because we're all used to talking about watts. Watts, 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 watts. The reason watts is useful is because if I'm going to buy 2 different speakers, I know that one of them can do 100 watts and one of them can do 200 watts. Well, that means the one that can do 200 watts is going to have more power coming out of it, right? But that's just what the speaker can do. That's what the speaker can do right there hooked up to your stereo. That's what the speaker can output. That says nothing at all about what it sounds like when you're 150 meters away from it. That is going to come into the realm of sound intensity because the power coming out of that speaker is going to be divided up over the surface area. Usually it's a spherical surface area there. And so you're going to get watts per square meter, which means literally if I take 1 square meter at that point I'm standing, then I'm going to know how many watts are flowing through that square meter, and that's going to be my intensity. If I increase any one of these quantities, the density of the air, the velocity of sound, any of these things, the intensity will increase. Now, that is one half of this lecture. This is basically one of the equations that you'll have to know, and I'm trying to beat it in exactly what it means so you're not confused by it. We'll do some problems and show you what it means. The other part of the lecture here is kind of related. Intensity tells us, pretty much everything we need to know. It tells us how much energy or power really is flowing through a surface area, a unit surface area there, and we're going to do problems that are going to show how to calculate that. It turns out that the human ear is actually capable of listening to an incredible range of sounds. It's really a marvelous little instrument that is in our head, and we totally take it for granted. You'll appreciate it more if you ever try to build electronic systems that detect sound or detect like a camera to take pictures or anything like that. You'll get a real appreciation for what your body can do, because the human ear is capable of listening to the most minute whisper. Very, 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 very quiet. You can hear a pin drop. If you get in a really quiet room, you can hear very, very, very faint sounds, all the way up to the roar of a jet engine. And through that entire range, we're able to listen to everything in between in those intensities. So it's a very good instrument at listening to very, very weak signals and very, very intense signals. Of course, you go too high, then you actually can rupture your eardrum and get permanent damage. But it's very, very good at that. So we could express all of the sound in terms of intensity, and that would be fine to do. But because the ear is capable of listening to such a broad spectrum of sound as far as the intensity goes, we actually invent a new scale that's related to the intensity, and we call it the sound level. It's not hard. You just need to take it one step at a time, and you'll understand what it means. Most of you have probably heard of the term decibels. I know that you might have seen before that a certain sound has so many decibels. Well, basically, I'm going to show you how to calculate decibels and how it relates to the intensity here, and you're going to see it's not really a big deal. Let's go ahead and do that now. Let's talk about the sound level. All right, again, without proof, because there's nothing to prove here. This is just a definition scientists and physicists created. The sound level beta is equal to the number 10 times the logarithm, and this is a base 10 logarithm of I, which is the intensity of the sound we're talking about, divided by I naught. And I naught is just a number that we're going to talk about here in a second. I naught, this is going to give you in decibels, dB right here. When you do this calculation, 10 times the log of I over I naught, you're going to get a number in decibels. So this is what you're talking about whenever you talk about decibels or have a decibel meter. I naught is just a number. It's 10 to the minus 12 watts per square meter. It's just a reference intensity. So for all practical purposes, this is 10 times the log of whatever intensity you're talking about divided by this number. So you would take this divided by this, take the log, so I can put this in parentheses to make it clear, multiply by 10, out spits a decibel. So this is a reference intensity. So you see, this sound level business is nothing more than taking whatever intensity you have, which is watts per square meter, and converting it to decibels. It's a way to convert that. The reason you do that is because, like I said, we have the ears, which are incredibly capable of listening to very weak and very intense sounds. So instead of having these intensities that were really, really tiny and really, really big as numbers, we choose a log scale. So you're doing nothing more than converting it to a log scale, and in a second you'll see that that makes the numbers a lot kind of easier to grasp. In order to see that, let me write a few things down for you, just to give you a feel for what the decibel really means. If you hear leaves rustling, then that's going to be roughly equal to 10 decibels. So a reasonable number, okay? If you're listening to a whisper, that's going to be roughly 20 decibels, or dB you might hear. A regular old conversation might be 60 dB. A rock concert, getting very loud here, might be 110 decibels. And just one more example, a jet engine, something very loud, something that's so loud you can't even hear yourself think, might be 130 dB, right? This is just to give you a flavor for what the decibel scale is. Now, if you go above jet engine too far, you're just going to damage your ears and break your eardrums. But you see the scale is nice and convenient. It roughly goes from 0 or 10 up till just past 100. It's a very convenient scale. We could list all of the sound intensities here in terms of watts per square meter, and we could do that for all of these things, but you would have really, really small numbers and really, really huge numbers, and that just becomes cumbersome when you're talking to people about sound, intensity. So we just invent this other scale, which is nothing more than converting these numbers to intensity to sound level in terms of decibels, and you get a nice convenient scale there. So don't think that these two things are different. They're not different. They're exactly the same thing. This is telling you how intense the sound is at your location, which is nothing more than how much energy is really going through that surface area at your location, right? And of course, we're just converting that to dB to get a scale that's convenient for us to work with. These are the two equations that are really going to be used in this section. There's nothing more than that. So what we're going to do now is erase the board, and we'll work a few problems and give you a feel for how to use these equations to solve problems involving sound intensity and sound level. Okay, the first problem goes like this. Sound with a spherical wavefront is sent out by a 1-watt source. First part of the question says, what is the intensity at 1 meter away? In other words, the sound intensity at 1 meter away. So we know that that we have this a speaker, or I'm just going to put a dot here because it's a spherical source here. It's shooting waves in all directions, and it's 1 watt, right? And I know that I'm 1 meter away, and I'm trying to find out what intensity sound I actually have right there. But I know that these wavefronts are spreading out spherically, and so 1 meter away, I'm basically sitting on the edge of a sphere, that's that big going all the way around it. And these wavefronts have expanded to that point. So if I'm trying to calculate the intensity, I'm going to be interested in the power emitted by the source divided by the surface area at the location where I'm actually sitting. So that would be 1 watt per, and I have to have the area of the sphere, which is 4 pi r squared. And so I'm going to plug in my radius, 1 divided by 4 pi 1 squared. And that's going to be 1 divided by, when you take 4 times pi times 1, you're going to get 12.56. And so the intensity of the sound at that point is only 0.080 watts per meter squared. And what this means is that if I'm standing at this location 1 meter away and I take my cardboard box, which is exactly 1 meter by 1 meter, so it's 1 square meter I'm holding out there, right? And I sit there and I somehow can measure how many watts are flowing only through that box, that 1 square meter box. It's going to be 0.08 watts flowing through that box because it's watts per square meter. That means this many watts for every square meter out here. Okay, for every square meter out there, that's how much power is flowing through that point. And that's because the 1 watt has spread itself thin as it's traveled out from the source. The second part of the problem says, what is the intensity at 2.5 meters distant from the source? So obviously, if I'm 2.5 meters, I'm not going to draw this to scale, but this is 2.5 meters, let's say. Well, I'm going to get in trouble here because I'm going to get in the way here, but you can see that this sphere is much, much, much bigger. Right? It's much, 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 much bigger. So the surface area that this second sphere encompasses is much, much greater. So my intensity, of course, is going to be lower. Let's calculate what it is. The intensity is going to be the power emitted by the source divided by the surface area, which is 1 watt, that's why I put a 1 here, divided by 4 pi r squared. That's the surface area, and r in this case is 2.5 meters. So it's 2.5 squared. So I'm going to get 1 over 78.5, and so the intensity of the sound when I do that division is 0.013 watts per meter squared. And if you notice, the intensity that I calculated at 0.013 watts per square meter is less than this out here substantially, because it makes sense because you're farther away. And that's exactly because basically you have to have conservation of energy going on here. There's only 1 watt, which if you remember back from your basic physics, what is a watt? It's a joule per second. Joule is actually the unit of energy. And 1 watt means that you're sending out a joule every second. 1 more joule, 1 more joule, 1 more joule, 1 more joule, coming out every second. 1 more joule. Well, a light bulb that's 60 watts means 60 joules coming out every second. 60 more watts. I'm sorry, 60 more joules, 60 more joules, 60 more joules. Every second, 60 more joules coming out in a light bulb. So this 1 watt guy means that every second I'm sending a joule of energy. So out here, the power here has expanded, and so you have conservation of energy. You always have to have conservation of energy. You can't get something for nothing. This energy must spread out to evenly cover this surface area here. And you can kind of think of it exactly as it actually occurs. It's a wavefront that's expanding because the compression of the air itself is expanding. So of course, if you're compressing the air a little bit to make your wavefront, and then you take that and you stretch it huge because you're expanding it out, well then obviously the little pressure differential in your little compression band of air is going down as the wave gets bigger because it's spread out so much. The molecules are actually spreading a little bit farther apart, and the intensity of the collisions are getting less and less as you go farther away. So this 1 watt is spreading out along this surface area. Of course, if it gets even farther away, it's spreading out even more. But the total power coming out of the source can be no greater than this, so of course your intensity has to go down. And that's exactly what this is showing you here. Okay. Now, the second problem is pretty interesting, I think. It says, a microphone in the ocean listens for whales. In order to register on the microphone, the sound must be at least 10 decibels when it gets to the microphone. If the whale emits a sound with a power of 0.05 watts, how far away can you be and still hear the wave? I'm sorry, yeah, still hear the whale. So what you have is a whale and you have a microphone. And we know that this microphone, it only has a certain sensitivity, which by the way, most real devices you build do have just a sensitivity below which they won't work at all. So this microphone isn't going to register squat if the intensity of the sound coming to it is less than 10 decibel. It has to be greater than that. So what we need to do is figure out how far away can that whale be and still give you a signal at 10 decibels. It's instructive to draw a picture if it helps you. So, you might have a humpback whale here. That's a whale, believe it or not. That kind of looks like a genie lamp or something, but it's supposed to be a whale. And over here, a microphone. Underwater, right? And of course, it's a certain distance away. So we're going to do that here. We're going to say that it's a distance r away, let's call it. Okay, and that's a distance we're trying to actually solve for. How far away can the whale be? But we know that the intensity must be, or we know the sound level must be 10 decibels right here at the microphone. Otherwise, it's not going to register anything. So we go ahead and start by writing down what is the equation for the sound level. It's 10 times the log of the intensity of the sound divided by I naught. In other words, if I'm trying to calculate how the sound level here that this wave is emitting, I need to know what the intensity is from the whale as it has reached this point, and then I can calculate 10 dB. But I don't really know what I is yet, so I'm going to go ahead and calculate that first. So I'm going to put 10 dB down because that's the sound level I'm shooting for. 10 log of I divided by, and I naught is just a number, 10 to the minus 12. You can just stick that right in there. So what I'm going to solve for here is I, which is the actual intensity of the sound I at this point. 10 cancels with 10. So you have 1 equals log of I divided by 10 to the negative 12. To solve this guy, you want to raise both sides of this equation to the power of 10. If you don't remember that from your trig or pre-calculus, you can always do that. Anytime you have a log on both sides, this is a base 10 log. So if I took 10 to the power of 1 on the left and 10 to the power of log whatever's on the inside on the right, raising both sides to the power of 10, Then on this side, log is going to cancel with log, so on the right-hand side, I'm just going to be left with what's on the inside, and that's what I'm trying to do. And on this side, I'm going to have 10 to the 1, which is 10. So I basically get rid of log by raising both sides to the power of 10. The intensity I'm going to get here is going to be 10 multiplied by this number here, which is going to be 10 to the minus 11 watts per meter squared. This is the intensity of the sound that this whale has emitted at the microphone. But that's not what I was trying to calculate. I'm trying to figure out how far away I can be. So I need to take this information and put it into what I know the intensity of these waves are, which is the power emitted divided by the area. So I know the intensity of the sound that I can have there is 10 to the minus 11. And the power emitted by the whale is given in the problem as 0.05 watts. And the surface area here, you see if the wave emits a sound that expands like this, I'm sitting on the edge of a sphere with area 4 pi r squared. So you see this is the intensity of the sound that the whale has at that microphone. This is the power emitted, and this is the surface area. So we have enough information to proceed. We take this denominator and multiply it over here, and we're going to get 1.26 times 10 to the minus 10 r squared, and that's going to be equal to 0.05, because this number 10 to the minus 11 times 4 times pi gives us this. R squared comes along for the ride, and so then r squared, when I divide both sides by this number, is going to be 3.98 times 10 to the 8. And so taking the square root of both sides, I'm going to get 20,000 meters, which of course you know is 20 kilometers. So that means that this whale can actually be 20 kilometers away. If he's farther away than this, the intensity is going to drop so low that I'm going to have less than 10 dB at the microphone. I'm not going to be able to register this sound at all. If I have an intensity, if I'm closer than this, then I'm going to be in good shape for that microphone to detect this whale. Okay, our next problem says a speaker produces sound with a frequency of 2,000 hertz and an intensity of 0.960 watts per square meter. That's milliwatts per square meter at a distance of 6.1 meters. Question is, what is the intensity of the sound at 30 meters? So I'm given some information, I'm given the frequency, I'm given the intensity, I know how far away I'm standing, but I want to calculate what is the intensity at 30 meters away. So you need to start out from the basics, which I told you, there's only two equations in this section. The intensity is always going to be the power per unit area. Well, let's go ahead and calculate what we know how to calculate. Let's put in what we know from this problem and see where it takes us. The intensity of the sound was given by 0.960 milliwatts per square meter. So let's put that in for I, but we never want to work in milliwatts per square meter. You always want to work in 960. We're going to write it as 10 to the minus 3. 0.960, it's milliwatts, but instead of putting milliwatts here, I'm going to put 10 to the minus 3. So I'm always going to work in watts per square meters. So this is watts per square meter. And I basically converted from what the problem gave us here. That's one of the tricks in this problem. It's equal to the power divided by the surface area. Now I know I'm at a distance of 6.1 meters, so that's going to be 4 pi r squared, so it's going to be 6.1 squared. Okay, 6.1 squared. So basically this is going to allow me to calculate the power emanated by the source, and that's going to help me in the second part of the problem. P is going to equal this number, 0.96 times 10 to the minus 3, times 4, times pi, times 6.1 squared. And what you will get is 0.45 watts. This is how many watts this speaker is actually outputting. It's an intermediate step needed. And what we're going to do is now calculate the intensity at 30 meters. 30 meters away. And that's going to be the power emanated divided by the surface area at whatever distance you're at. Now we know the power emanated by the source for 0.45 watts. And we know that we want to be 30 meters away. So that's 4 pi times 30 squared, because everything is expanding in a sphere. Remember I told you that at the beginning of the section. You're going to see that a lot. This is the surface area of that sphere 30 meters away. So what you're going to have is 0.45 divided by 4 times pi times 30 squared is 11304. So the intensity will be 3.97 times 10 to the minus 5 watts per square meter. Watts per square meter. And if you wanted to convert that back, because you have an ugly, scientific notation here, that's the same thing as 39.7 microwatts per square meter. You see, this is 10 to the minus 5. If I move the decimal one space this way, it'll be 10 to the minus 6, so 39.7 microwatts, because micro is 10 to the minus 6. So you can see that the intensity here at a much closer range is much, much greater than the intensity way out farther, and that's just simply because, well, it's common sense, the sound is going to sound less the farther away you get, but it's because those wavefronts are expanding and moving outward in space, and so you're going to have a lower intensity out farther away that you get. So that concludes this section on sound intensity and sound level. And it's really nothing more than trying to take into account that when you launch an actual sound wave, very rarely is it moving in one linear direction. Usually it's expanding spherically, and that just kind of makes sense. If I talk here, no matter where I'm standing around me, up, above, or below, or to the sides, I can usually hear what I'm saying. That's because the wavefronts are expanding spherically. So in order to figure out what something is going to actually sound like, you need to take that into account. And it's always going to be equal to the power emanated by the source divided by the surface area where I'm standing. And that's going to give me a unit of watts per square meter. So if I stand here and I'm listening to a source come in and I have a square meter box and I see how many watts come through that box, which is how many joules per second come through that box, which is a square meter, that is the sound intensity. Obviously, the farther away I move, the farther the wave has expanded into a larger and larger sphere, and so the power has become thinly distributed along that sphere, and that's why the intensity is lower. Now, the sound level is absolutely nothing different than trying to describe exactly the same thing. It's just applying a logarithmic scale to the intensity, right? Because our ears can listen to very low whisper sounds and very, very loud sounds. So instead of writing a bunch of intensities of 10 to the minus 5 and 10 to the minus 3 and watts per this, per that, we convert it to decibels because it kind of makes sense that at the low end of human hearing, we'll have, maybe 5 or 10 decibels, and at the upper end of human hearing, we might have 130, 140 decibels. Everything in between is everything we can hear, so it's a convenient way to express sound level to other people. I'm Jason. I hope you've gotten something out of this section. Practice your problems. There's only a few concepts in this section. Once you realize what intensity and sound level are really trying to do, the concepts really are not that hard. Learn anything at mathandscience.com.